On some clear days with no clouds, I take a short glimpse toward the sun and am struck by how enormous and brilliant it appears in our sky. The fact that it affects us here on Earth so significantly despite being millions of kilometers away is difficult to comprehend. Without the sun, there would be no life. The light and energy it supplies are the source of almost everything. There is still a lot we don't know about the sun, despite the fact that it is not particularly difficult to see and is pretty close to us. For this reason, both NASA and ESA have launched spacecraft to investigate the sun. Now as we talk, on 2nd of September, Indian Space Research Organization has also launched its spacecraft for the observation of Sun's corona. We are now closer to our star than ever before. Enough close, in fact, that some of them will be able to directly interact with Sun's atmosphere. So the question is, why are we sending so many probes to the Sun, and what makes each of these missions unique? In this video, we will see how NASA's Parker Solar Probe and ESA's Solar Orbiter will explore our own magnificent star, the Sun. A Delta IV Heavy rocket was used to launch the Parker Solar Probe on August 12, 2018. After it was first announced in 2009. It will progressively reduce its orbital diameter by making 7 flybys of Venus over a period of almost 7 years. It will be inside the Sun's corona or atmosphere, and barely 6.16 million kilometers away at its closest point. When you are that near, it feels like there are 500 suns pounding down on you at once. And the temperature can get as high as 1400 degrees Celsius. Many of the components used to create sensitive technology for spacecraft would melt away at these temperatures. Because the spaceship is traveling 7 times closer to the Sun than any other spacecraft has gone ever before. The spacecraft is insulated by an 11-centimeter thick carbon composite shield, which can survive extremely high temperatures, to protect it and all of its equipment. The white reflective surface of this shield can reduce heat absorption. This shield will defend the spaceship from the hostile environment by facing the Sun at all times. Due to its distance from Earth and the fact that it is orbiting dangerously close to the star, this spacecraft is as independent as any space mission has ever been. It won't be able to point its antenna at Earth for significant portions of its orbit since the heat shield must always face the Sun. When there is a communication blackout, it will maintain control over all of the sensors, manage the formatting of data products, and store high-resolution data until it is able to re-establish communication with Earth and send back the images it has taken. After 8 years of development, the Solar Orbiter mission of ESA was launched on February 2020, using an Atlas V rocket.
Of our solar orbiter and international collaboration to give us new images.
The Solar Orbiter will use the gravity support of Venus and Earth to put itself in Sun's orbit. The Solar Orbiter will begin its orbit around the Sun after these swingbys, which will last 180 days. Every 6 months, the spacecraft will be approximately 43 million kilometers from the Sun as it makes its closest approach. The sunlight will be 13 times more strong than it is on Earth. Therefore, the temperature might exceed 500 degrees Celsius at this distance of around 43 million kilometers from the Sun. Although less effective than the heat shield of the Parker Solar Probe, the Solar Orbiter's heat shield of titanium foil layers around 40 centimeters thick is more than sufficient to shield the spacecraft during its dangerous mission. Given that it requires 55 times more energy to travel to the Sun than it does to travel to Mars, it is quite challenging to place a probe in a near orbit around the Sun. You see, the Earth is constantly moving sideways in relation to the Sun at incredibly fast speeds, roughly 30 kilometers per second or 108,000 kilometers per hour. A probe needs to almost entirely cancel out that motion in order to effectively enter an orbit around the Sun. Because of this, the Atlas V and Delta IV, 2 of the most potent launch vehicles at the time, were used to launch both the Parker and Solar probes. Both of these missions are designed to learn more about the solar wind, coronal mass ejections, magnetic field structure, solar corona, and how everything works together. The Sun is a ball of plasma, just like all other stars. Plasma is extremely hot matter that is so intense that it strips the electrons from the atoms, leaving an ionized gas. The Sun's corona is an atmosphere extended out millions of kilometers and made of incredibly hot plasma. Although the plasma atmosphere is usually far more difficult to view than the Sun itself because of the Sun's brighter photosphere. The best moment to observe the Sun's corona is during a solar eclipse, when the Moon obstructs the photosphere disk and only the thin coronal arms are visible. The temperature of the Sun's corona, which ranges from 1 million to 3 million degrees Celsius, is strangely higher than that of the Sun's surface, which is only approximately 5,500 degrees Celsius. Currently, we are unsure of the reason. The corona of the Sun appears massive, but its brilliance is deceptive. It is far less dense than the atmosphere of Earth. The solar wind is the continuous, enormous discharge of plasma and radiation from the Sun into space. The majority of the solar wind is safely diverted away by the Earth's magnetic field since it is not extremely powerful or dense. While much of the solar wind is diverted around the globe, part of it is directed towards the poles. Here, solar wind ions mix with atmospheric oxygen and nitrogen atoms to produce the stunning colors we see in auroras. The quantity of particles released by the Sun varies. Large quantities of energy can be released during magnetic field reconnection events on the Sun, which can cause the corona to erupt violently with millions of tons of charged particles. This is called a CME, or coronal mass ejection. A geomagnetic storm is created when these CMEs impact with the Earth's magnetosphere, and the worst of these storms can be catastrophic. The Carrington event in 1859 was the biggest geomagnetic storm to ever affect Earth. If such storm hits Earth right now, might have catastrophic effects on satellites and our electrical grid. According to some projections, a Carrington-scale disaster may result in several $1 trillion in losses if it occurred today. Sadly, CME flares move quickly. They have been demonstrated to arrive on Earth in about 17 hours. There may not be enough time to warn everyone, shut down the reactors, and take other necessary safety measures. Since we were 9 days away from being slammed by a Carrington-sized event in July 2012, we have merely been fortunate up to this moment. If it had occurred 9 days later, Earth would have been a little farther along in its orbit and in the path of the CME. Because of this, it is crucial for us to comprehend the Sun's corona in order to forecast solar storms more accurately, and provide greater warning from an actual Carrington-scale catastrophe striking Earth. The Parker probe is entering the Sun's corona at depths never before reached by a man-made object. The spaceship is constrained in certain ways because of the extreme temperatures it must endure. For instance, it is unable to capture images of the Sun since no camera available today can gaze directly at the Sun from that close and remain alive. The Parker probe, however, is equipped with tools that allow for up-close examination of the regions where solar winds originate, and direct sampling and data collection about the particles that exist in the Sun's corona. In comparison to the solar orbiter, the Parker probe is lighter, smaller, and equipped with less technology. The solar orbiter, on the other hand, is equipped with telescopes and particle detectors. Due to its orbit, it will be able to track a region of the solar atmosphere for far longer than is conceivable from Earth. It can also snap up-close photographs of the interesting solar landscapes. As a result, it will be able to watch storms develop over several days. Speaking of accomplishments, the Parker probe came the closest to our star ever, traveling within 13.5 million kilometers of it on September 27, 2020. It also broke the record for the fastest human-made object ever when it reached a speed of 466,000 kilometers per hour. Even now, it's not even close to or moving as quickly as it will. Even yet, the information returned by the Parker probe is already advancing our knowledge of how the Sun's magnetic field and corona interact to produce solar winds. The probe also found that the solar atmosphere is swept by some magnetic fields from the Sun, which can accelerate the solar wind to a maximum speed of 5 lakh km per hour. A zone free of dust was also found to exist 5.6 million kilometers from the Sun. This is thought to be caused by the vaporization of cosmic dust particles by the Sun's radiation. You may view the so-called campfires that scientists discovered when the solar spacecraft returned its first photographs of the Sun. These are surface-level explosions on the Sun brought on by changes in tiny magnetic fields. The solar orbiter also captured the Sun's surface from a distance of 77 million kilometers in its closest ever photographs. Consequently, as we go closer and closer to the Sun, we will learn more and more about it. Thanks for watching. If you find this video interesting, please consider a like and don't forget to subscribe. See you next time.